Good morning, everybody. Thank you for joining us this morning. My name is Cale Harbor. I am the product manager here at Advanced Control Solutions. And today we're going to be going into a hands-on example of how to use the Epson robot simulator to be able to help with some cycle time studies, make you aware of some of the basic features, and also be able to look at a few of the ways that we can optimize the system in order to be able to pick up a little bit of cycle time, speed, and efficiencies with it. So I'm waiting on everyone to log into the room. It looks like we've just about got everybody. If someone could just shoot me a quick message in the chat window just to make sure the audio is coming through all right, I would appreciate the confirmation. There are still a couple people coming in from the lobby, so we'll give it just another second. So as the event goes on today, if you have questions that come up, awesome. Thanks to everybody letting me know. Glad to know the audio is coming through. Appreciate that. But as we come through, if questions come up, please put the questions into the chat room. I'll be happy to go through everything that I can today, be able to answer that for you. And if we have time, be able to show you a little bit of the command structure that goes with it. Now, just to let you know, the normal programming class for Epson is a multi-day class. Then when you add the simulator on top of it, there's actually a fair bit that goes with it. There's no way in the next half hour we're going to be able to go through anywhere near the full list of commands and command structures on how to navigate. So in order to make sure that we get the best use of the day and that we get the material covered on the basics as efficiently as possible, I've gone ahead and opened up my version of Epson RC Plus software. So I'm making a couple of leaps of faith that many of you are already familiar with the RC Plus programming environment. It's something that you have worked in before. If you have not worked in this environment and you are interested in some additional programming training, I am going to throw up a quick poll just to try and get a feedback from everybody of who's interested in actually attending a more detailed programming course. The poll should be showing up now. If you are interested in it, please let me know on the feedback for that. I would appreciate it. So with the assumption that you already have at least seen RC Plus software, at least a little bit familiar with it, this is the programming environment that we're going to work in for the Epson robots. This is what's going to contain our point files, our coding, our I/O control, our jog and teach screens, everything associated here. So within this environment, and the main topic of today, we do have available to us the ability to connect not just to a live robot. If you can see my cursor up here, I'm currently offline right now. I have the ability to log into a live robot either through a USB cable, or I could log in through an Ethernet connection. But I also have a list of, and you can see my list, I've actually added a variety of them, different virtual robots. This allows me to be able to test my commands, my programming, teach my point files, even interact with the vision system built into the capabilities if I have those images saved, all within a virtual environment without having to be hooked up to the live robot itself. So one example that I was going to show you up just real quick, the software is going to pre-install with several robots already configured. So I can immediately log on to a C4 or an N2 or a G6 and bring up those characteristics associated with it. So right now, what I've done is I've chosen the N2 as an example this morning. This is a very unique compact folding 6-axis. And now that I've logged into that controller, I can actually choose the simulator up here from the toolbar. So the simulator has 3 small icons built into it. It shows also the shortcut key, the Control F5 to be able to get to it. And you can see that I now have a simulated environment where I have my robot. And I can manipulate this just like any other CAD file using my left and right mouse buttons. So I can pan, tilt, zoom as I need to. Now you notice this particular robot happens to be in a ceiling mount configuration. So it is attached to my 0 plane up above, and then the robot hangs underneath it. From here, I can then be able to manipulate the robot and make it move around in space. Well, one of the things that commonly comes up, there's only a handful of robots that come pre-configured from Epson within the RC Plus software. In order to get an application up and running, many times I'll have to set up a new robot within the virtual world. So I wanted to walk you through that process on how you achieve that. So the way that I would set up a new robot, I'm just going to go back offline. So it's going to shut down from this virtual controller, and I'm going to start over from the beginning. I would come under Setup, and then I come under PC to Controller Communications. This is what allows me to set up my communications with, in this case, I can show you the example of number 8 here. This is an Ethernet address. So now I can create a connection to talk to a robot via an Ethernet connection. There's also the standard USB connection up here in number 1 slot, where I can use the USB cable from my PC to my robot. But all of the others that you see here are virtual. These are my virtual robots that I can be able to work to within simulator mode. So let's say, for example, there's a robot I want to work with, I don't have it set up, and I need to be able to create it. So what I would do is I would hit the button that says Add. I get asked the questions. Do I want to connect to a real robot via an Ethernet, or do I want to connect to a virtual? In this case, we're going to connect to a virtual controller. So I'm going to say OK. So now I have added this virtual controller. I can now go in and I can name this. So what I'm going to do is the robot I'm going to work with this morning is going to be a G20. And since it's for the webinar, I'm actually going to create it to say G20 webinar. And then I'm going to hit apply, and it puts my changes in there. So now I have this created. So it is now part of my list. If I close the window, I can come back to my drop down. And as I scroll through it, you'll see that down here at the bottom is the G20 webinar. This is that virtual robot I just created. So what I'm going to do is now log into it. Now, one of the things that you may have noticed is all I've done is given it a name. I've told it it's a virtual machine. I haven't actually told it what robot I'm working with yet. That's one of the important things that we need to do. Now that I'm connected to this virtual controller, I need to tell it which robot I want to work with. So in this case, I'm going to choose Setup. I'm going to go under System Configuration. And under the system configuration, this is going to be all of the normal setup options that you would expect to have when deploying a system. Are you running Vision? What type of security? What's your Windows password? The IP address associated? Startup in automatic or program mode? All those other options that you would associate in deploying a live automation project. What we want to do, though, is go under the controller, and I want to be able to go under robots. I'm already underneath a virtual controller because I've already created as a virtual. Now I want to tell it what robots I have. And you'll notice currently there are no robots set up within the system. So what I'm now going to do is add a robot. Now this is actually really useful because I can add and take away robots as I need to work with in a test mode. So in this particular case, it's asking me for a name. I'm going to be working with a G20, and I'm going to have this be the 1 meter arm. So I'm going to call that a G20A. The A is the nomenclature used to call out a 1 meter arm. I do have to give it a serial number. Now, since this is a virtual machine, I don't have a live serial number. I normally just put in a few zeros to represent my serial number, and it will accept that. The motion system, we're just using a standard motion system. I don't need to change anything there. One thing I do need to explain is this one, the drive unit. So as I'm working in the RC Plus environment and then with the Epson controllers, specifically their RC 700 series controller, that controller, that family, this software has the capability of running multiple robots off of a single controller. One unit has to be declared a CU, a control unit. Pardon me. That's what's going to hold our program. That's what's going to hold our information, our point files, our accessories, our vision interface, conveyor track interface, whatever I'm working with is going to be in the control unit for those options. The RC700 can control up to 4 robots from that controller. Robot 2 would then have to be set up as DU1, drive unit number 1. The third robot would be drive unit number 2, and the fourth robot would be drive unit number 3. So by doing this, I can create up to 4 robots within the simulator and run all 4 robots simultaneously for cycle time tests, performance tests, whatever it is I need to work with. In our case this morning, we're just going to use a single robot. So I'm going to leave this set as the CU control unit. The next option, I can choose a SCARA. I could choose an Epson 6-axis robot, and you'll notice my image changes. Or I could change over to the easy modules. The easy modules are linear modules that we can use as a Cartesian robot, or allow it to be a 7th axis for either a SCARA or a 6-axis. And since I can control multiple robots within one setting, I can literally put my easy module, put my robot in, attach them together, and run them within the one simulator. For the purpose of our example this morning, we're going to be working with a G20 SCARA. So I'm just going to leave this set up as SCARA, and I'm going to come to my series, and I'm going to choose the G20 right here in the list. So G20-2, this is actually representative of the Roman numeral 2, 2nd generation G20 arm. So now that I've chosen my robot, it gives me a picture of what it looks like. I can now choose the particular model. Now, this is one of those things that is both a benefit, but sometimes a little overwhelming within Epson. Within the environment, we have hundreds of different robot arms we can choose. Different length reaches, different length quills, protected washdown, clean room, ceiling mount, wall mount, tabletop mount, all sorts of different options that we can be able to work with. So you have to understand a little bit how the part number works. The G20, it's a 20 kilogram SCARA. I have an 8.5, 850 millimeter arm, or the A0, which is the 1 meter arm. You notice I have an option between a 1 or a 4 in the next position. So if I look up at the top, this G20 851 versus the 854, the 1 is the standard length quill, the 4 is the long stroke quill. Then I have the option for a standard or an IP65 protected or a clean room version of the unit. That would be the next letter, S standard, P protected, C for clean room. The other thing that you'll see is an R or a W. W is a wall mount, R is the ceiling mount. So once you understand a little bit about the nomenclature, it's fairly easy to be able to pick what we want. The example we're working with is just the 1 meter arm, standard tabletop mount. So I'm now going to say, okay, that this is the robot I want to work with. Again, as this is rebooting and loading those characteristics, I'm just going to check the chat window right quick. Oh, someone let me know I forgot to hit the publish button on the poll. I apologize for that, y'all. The poll should now be up to let y'all interact if you are interested or not in additional programming training. So what's happening and what we have going on right now is we're loading the characteristics of this robot into my virtual controller. So now that that's in, I can come back here to my simulator, and when I pull it up, I now have my G20 robot that's actually physically appearing in my simulator. So I'm going to zoom out from this guy just a little bit. Now there's several things I can do with this arm while I'm in place within the simulator itself. One of the things I could do is I could bring in the CAD drawing of my machine that I'm going to put it in. I can bring it in as a VRML, a step file, an IGES, a DXF, an XV3. Then I can place the robot on the live machine frame that I would want to be working with. I can also attach the hand. The hand merely allows me to bring in my custom end of arm tooling. So let's say I have designed a piece of end of arm tooling that has 2 pneumatic grippers on it. I can load that in and it will attach it to the tooling plate. In the case of this Scara, it would be the end of the quill. By attaching it to that surface, then my end of arm tooling is going to move with the robot through space, and I can test for collision. Am I going to hit something? How much clearance do I need to be able to have? What moves do I need to be able to put in to get the tooling to clear an obstacle that might be in the machine, a guard, a frame, a post, or the like. So I have the ability to bring those straight in. One of the common things that I use this for is I might want to simulate an in-feed and an out-feed conveyor for a particular application. So what I can now do is come in under the plane, and I'm going to grab this button that says Layout Box. And you notice I have a box here on the screen. So this box on the screen, I can very quickly turn into an in-feed conveyor. What I would do is come into the settings of it, and you'll notice there's a setting called half size. This allows me to put in the dimension from the center line to the edge of the object. Now my coordinate system is a XYZ coordinate, but that's based off of the same XYZ world coordinate of the robot. So if I look at the robot so that the back of the robot is facing me, then my y-axis, y plus is going to move away from me, y minus is going to move towards me. My x dimension is going to go across horizontally in this case. So let's say I want my in-feed conveyor that's coming in on my y-axis. So in this case, I'm going to make my conveyor 800 millimeters long. So I would put in 400 millimeters from my center point to the edge. I now have an 800 millimeter long conveyor. Let's say though, I want this to be 200 millimeters wide. I put in 100 millimeters on my X, and I now have something that's 200 millimeters wide, 800 millimeters long. But as I rotate this, this might be the thickness I need with my drive rollers. If I want something thinner or thicker, I can then come into the Z. Let's say I'm running a thinner conveyor at this point. Maybe I just want 20 millimeters thick. And again, because I'm putting in half size from the central point to the edge, I can now thin the conveyor out. Well, I really want my in-feed conveyor back over in this area, so I need to move it back. So this is where I'm going to go into the position of it. So right now my center point is 550 millimeters in the y-axis by 550 millimeters over in the x. And I'm 25 millimeters from the height of my plane. Well, really, I want this to come backwards along the y-axis. So I'm just going to make this 0. You notice it puts the center of the conveyor in line with my y-axis at the 0 position. If I really want this to be entirely behind it, I'm going to put in -400. So now my conveyor, the center point, is 400 millimeters behind the 0 point of my y-axis. So this allows me to get my in-feed conveyor. You notice it's stopping right at the center point. Now I can have it for my pickup. I could then repeat this process for out-feed conveyors. I can tie them together to make a conveyor loop, but I can put my targets in here. By manipulating additional boxes, I could put in side rails, or I could raise or lower the height as needed. So I can very quickly, if I just need to do a cycle time study, which is what we're going to work on this morning, I could very quickly put in representative shapes within the environment without having to generate a complete CAD drawing for it. This particular case, because I do want to be sensitive to time, I am going to leave this just like it is with just the in-feed conveyor. And then I'm going to hit my save button up here on my toolbar to then save this in place. So I'm now going to minimize this. Now I want to take a look at the program that I have going on. So this is the program that I have in place, and I wrote this to save time for us this morning. If anybody has questions that we need to get into, I'll be happy to answer those questions or send additional information to you. Just let me know in the chat window. I see over here that I do have a message that come in. Would it be possible to show the manual part number build out? I will try to pull up the screen for that to be able to show you as part of this, or I'll be following up in an email, Joseph. Thank you for sharing that. I'll get back to that one. So within the environment we have here, the RC Plus environment programs and function blocks. So I have a function here called main. My program's always going to begin in function main. I'm now going to call a subfunction, in this case, robot initialization, where I reset in case there was a flag, make sure my motors are on, go to a position that I know is a good, safe position to start with, put my power in high power mode, and set my speed and acceleration. This is the basics of what I need to get a program running. Then I call a function called pickPlace. pickPlace, I have a timer built in. I'm going to cycle it 5 times, and I'm going to be able to print what the overall cycle time is. So to show you how this runs, what I'm going to do is I'm going to put my simulator up side by side with my code, and I'm going to open the run window for the program, and I'm going to hit start. Are we ready to start? Yes, I am. So you notice as soon as I say ready to start, my simulator now begins moving. Arm has reached the end of its range of motion. So you notice I have an error that's come up here that I need to be able to see about. So I think what I have done in this case is the robot that I chose, I believe I chose the standard stroke quill. And when I wrote my program for the long stroke quill. But this actually shows part of the power of what RC Plus could do. Let's say in this case, the only thing that I have here, I'm going to stop running my program, is my error message at the bottom that says, I have an error. There's something gone wrong with it. We now have an error in the program, not sure what line that it's on. If I double click on this error message, it will take me to the line of code where I have the problem, and it tells me I have an issue with this jump pick. My Z-axis, joint 3, I have too low for the robot that I've chosen in my emulator. I now have an idea of what it is I need to fix. I need to fix that point. So what I'm going to do is pull up my robot manager. The robot manager contains all of my settings for my robot to be able to control range of motion, be able to teach points. I'm going to go to my point file, and you'll notice here I do have -300. So I'm going to shorten this up. I'm just going to say -180 for my Z-axis here. You can manually edit your point file. You don't have to move the robot over to reteach. So in this case, I'm just going to edit it and save that new point file. And let's see if that took care of my error. So I'm now going to reopen my run window, and I'm going to hit start. And that took care of my error. So you now notice my robot is moving. It's going to cycle this 5 times, and it's going from what I declared as my pick position over here on the side to my place position. And it is telling me that the first pick, going from my known safe position to my pick and my place, only took 2.2. But the normal production run, going from pick to place, I'm running about 3.1 seconds. So my total time for these 5 points is just under 15 seconds. Well, this is running in simulator. How do we know that this is accurate? This is where, and hopefully you notice this, within my code, I have a function called clock test. Anytime that you're working in the simulator, you want to check your clock to make sure that it's going to be accurate. The way that you would do that is create a function called clock test. I normally pull out my smartphone, I pull out my stopwatch, and what I would now do is from my run window, I'm going to choose the function labeled clock test, and I'm going to say start. At this point, I would start my stopwatch at the same moment in time that I start this function. So now all I'm doing is running this function. And all this function is doing is it's waiting for 30 seconds. And when it's finished, it's going to print the word done on the screen. So I sit here, have my finger over my stopwatch. I'm waiting for it to come in and say done. As soon as it says done, I'm going to stop the stopwatch and look to see if the time matches. You're never going to be 100% on time perfect with it, but if you're within plus or minus a second, you're going to be reliable enough to trust on this for cycle time. If you're beyond a second, you're going to need to adjust the clock settings within the Epson software in order to dial it in. And the settings for that can be found in the help file, but that is quickly under Setup, System Configuration, Controller, Simulator, and I would adjust the performance and precision numbers either up or down, depending on if I was too long or too short, in order to dial it in. One thing I will point out, since I've upgraded to Windows 10 and begun using it, I've not had to adjust those numbers. My clock has been very reliable for me, but you want to test it on your machine. Depending on what you have running in the background, it could be off. Now, once you make sure that your clock is synced, you're within that plus or minus 1 second. Cycle time analysis running the simulator is going to be plus or minus 15% of the real world. So when I go to look at those numbers, if you remember, we ran 14.85 seconds for my 5 pick and place points. Well, that 14.85 is plus or minus 15%. The only way to get the absolute down to the millisecond cycle time is to run it in a live robot, but you can do a lot of testing up front to see if you're going to hit your cycle time within just the simulator. Let's say, for example, though, if you remember our motion that we had when we ran the main program, and I'm going to zoom in on this guy a little bit. We're using the jump command. So our quill goes all the way up, we go all the way over, and we go all the way down. We don't begin moving in our horizontal fashion until our quill goes all the way up. Most of the time, in fact, the vast majority of the time, we can begin moving horizontally while we're still moving vertically once we clear our obstacle. So we can allow this to be a little more efficient. We don't have to wait as long to travel. The way we would do that is we would use the command called LIMZ. So if you notice within my program that I've got here, jump pick, jump place, if I add a space, LIMZ. Now, if you remember, I set my point, we're 180 millimeters down. Let's say I only want to come up 100 millimeters. So I'm going to limit my Z stroke to negative 100. Z strokes are always going to be a negative number. And this is saying that my quill is only going to come up to within 100 millimeters of joint or of my zero position for my quill. So I'm limiting that motion. Now I can tell you right now, this is going to give me an error. I'm going to go ahead and run that, let you see what the error is, because this is one that I usually make most of the time and then edit it later. So as soon as I say start and hit yes, you'll notice my program starts just like it did before. My robot is going to my known safe position. And when I say known safe position, this is just my programming standard. I like to have a point that I know I can start from and not run into a problem. And as predicted, you'll see I got an error. This is the exact error I was expecting. Current point position is above the LIMZ value. This is what that means. When you're working with LIMZ, you have to be aware of where your quill is when you call the LIMZ command. If I bring in my robot manager again and I take a look at my point file, you'll notice my start position is already or is at 0. So my point position is above what my LIMZ is. Well, it doesn't know how to deal with that. So we need to be able to address this. One thing I could do is I could come in and edit my Z value here, just like I did before. But I actually want to show you a different way that I can edit this. So what I can do is once I jump to start position, I can now say go here minus Z 100. So what I'm doing is I'm saying where I'm at, I want to lower my Z axis 100 millimeters. And actually I could probably, just to make sure, I could even go a little beyond that. I could go 101. This puts me below the LIMZ. Let's see how that behaves within the program now. So I'm going to recompile and I'm going to say start. Here's my quill coming down and then my program starts. So now as we look at the cycle time, if everybody remembers the time that I had before, we totaled out at 14.85 for the total count of 5. We're now at 13.03. Same speed, same acceleration. We've been able to pick up over or almost 2 seconds of cycle time. Well, let's go a little more. There's more we can do with this. Let's also say that in addition to limiting the Z stroke, we can also begin moving horizontally and vertically at the same time. It's known as the arch command. The arch command is denoted between the LIMZ and the jump with the letter C, and I'm going to say C1. So I'm using arch number 1. Well, what is arch number 1? Let's go back under our robot manager. Hopefully y'all are picking up a trend. We use the robot manager for a lot. Robot manager tells me that arch number 1 has a departure Z. I'm going to move up 40 millimeters before I begin moving horizontal. The approach Z, I'm going to have to be over my XY and begin moving straight down 40 millimeters above my destination. I could make this be whatever I need it to be for my application. So let's say I want my departure to be 20 and my approach to be 30. I can now apply that, and now those settings will go in place. Let's see what that does to us. So I'm going to rerun my program. And now we're going to have the LIMZ and we're going to have the arch together. So the two things that we have going on is we're limiting the stroke of the Z axis, but it also is going to begin moving horizontally and vertically once I come up from my surface just those few millimeters. So now instead of seeing it go all the way up and stop and have that dead time, we're now achieving both together, and we're going to pick up a little bit more in this. So now you notice by adding that, we've now gone from 14.85 on just the pure jump. We've gone to 13.08, adding the LIMZ. Now we've gone to right at 10.9. We've picked up an additional little over 2 seconds of cycle time just by adding the arch. So we're getting more efficient. Again, we're not changing the speeds, we're not changing the accelerations, we're getting more efficient in our movements. There's one more thing that I want to point out that is quite dramatic. I'm going to rerun this scenario again with this top view. And I want you to watch the motion of this. So the way I have this set up, most of our motion is located within joint 1, which is right here at the column. The arm itself is in what we would refer to as a righty configuration, meaning from the back of the robot to the front, the elbow is pointing on the right-hand side. Well, if you notice, almost all of the motion that's going on here is all centered around joint 1. Joint 1 is the slowest of the joints because of its gear ratio. Joint 2 is doing nothing. So in this particular case, maybe if we used a combination of arms, a righty and a lefty, maybe it'll affect our cycle time because now joint 2 and joint 1 would be moving simultaneously. So my pick is a great example to use as a lefty arm. The way I can force that is on the end of my command, I can say /L. And I think I put it in the wrong place. Nope, I had it in the correct place before. Sorry about that, y'all. So now I have this as a lefty. I have put an L here at the end. So now let's rerun this and see what this does for us. Build abort due to errors. Here's that error. Variable does not exist. So if you notice, my syntax is off. I have forgotten something, not doing something right, not declaring it right. I'm going to let the audience guess whether I'm doing this deliberately to show a point or if this is truly I have forgotten. But I can show another feature of RC Plus. So what I can do is, in order to get this correct, I'm going to need some help from the help file. If I put my cursor on the jump command and I hit my F1 key from the keyboard, it's going to take me to the help file for this joint statement. It's going to now let me go in and be able to spot, where did I get this wrong? What did I do that was incorrect with it? So if I scroll down to the bottom, I can be able to see some examples of how it gets used. So jumping to a point, I can declare my LIMZ. I have all of the other commands associated with this particular point or command line for jump. So I can limit my Z motion. We're already doing that. The arch, we're already doing that. So what I'm looking for is the command to be able to force it to be either a righty or a lefty. And I actually may have discovered something that I wasn't aware in this version of the software. The /L or /R is the command I'm used to using for this. Looks like either I have completely forgotten it or a command structure has changed I wasn't aware of. So now let's go back into the point file. We can easily finish this example this way. So I can actually change my pick position from a righty to a lefty. And let's resave that point. And we're going to restart the program. So now when the program starts, my quill's coming up, my robot's moving over. I didn't change my righty or lefty from the start position point, my known safe point. I only changed the pick. So as soon as I get to this position, notice it changed to a lefty, and now we have joints 1 and joint 2 working together. So both of them are achieving the motion to get to my XY where I need it. And you'll notice I've now dropped my cycle time to 9.27 seconds. So we've picked up another 3/4 of a second of cycle time. So we've taken this just with a few simple commands using the arch, using the LIMZ, then thinking about the righty and the lefty to make it more efficient. We've been able to get from 13.85 seconds to 9.27 seconds on my cycle time. But again, this is good to plus or minus 15%. If I knew that my cycle time on this needed to be within 11 or 12 seconds, I'd feel very good and confident this is going to achieve what I need it to do. If I needed to hit a 10-second cycle time, then I would say this looks promising. Let's do a little more testing. But this is a great example of how you can use the simulator in the design of your systems and your testing to be able to experiment with different commands and how you can pick up different efficiencies and affect your cycle time that you have going on with it. All right, we've run a little bit longer than I had planned. I'm looking at the chat window right quick. I'm going to be sending out a document to everybody afterwards that will go over the part number build sequence on how we build the part numbers. That was one of the questions that was asked. If anybody else has a question, please post that in the chat window now. I'm just going to take a quick look. Looks like 78% of you said that you are interested in additional Epson programming training. So to let you know, we are an authorized training center for Epson. We teach those classes here at our ACS training facility in Marietta, Georgia. There will be another Epson spell programming class coming up between now and the end of the year, as we are coming out of the COVID-19 pandemic and we're getting our class schedule back online. That is something that we are going to be adding back to our mix as the year goes on. We set that up with live robots where you're interacting with live robots, live I/O, actual pick and place, cycle time optimization going through the command structures. So if you have not visited our website before, our website is advancedcontrolinc.com. So I'm just going to real quickly take you to our website under our training tab, Epson Robot Programming. This is where we would be posting upcoming dates for that. So please check in here. It will also be in our newsletters and in our training emails that go out when we do add that to the schedule. I will be keeping up with everyone from the poll today that expressed an interest in it and make sure we reach out to you specifically when the time comes and I get that scheduled. In the meantime, if other questions come in, we're happy to help out with that. If there's no other questions and I don't see any coming from the chat room, I'm going to wish everyone an awesome day. If you do have additional questions that come up, please feel free to reach out to us at info@acs-ga.com. I hope everyone has a great day. Thank you for attending.